Okay, good morning. Welcome to a tutorial on complex numbers, section 4-8 of your Algebra 2 textbook. Okay, now complex numbers start with the concept of a number whose square is -1. Okay, so an imaginary unit, I, is the complex number whose square is -1. So I squared is -1, and I itself is equal to the square root of -1. In the past, we've said that if it's a square root of a negative number, there's no real solution. But today, we're going to talk about complex solutions. So here's a quick example in here. Okay, for any positive number a, okay, that you can go ahead and if it's a negative number, you'll break it down to the square root of -1 times the square root of a. So I can write it as I times the square root of a. For example, if the square root of -5, I'd have I root 5. The square root of -7, I'll break it down to the square root of 7 times the square root of -1. So I'm going to write I root 7. All right. And if I squared this, what's going to happen is I'll get a different kind of idea. So if I square something, it's going to be the same as multiplying it through. Okay, the square root of -5 squared will give you -5. So here's a quick conclusion. We have an entire category of numbers based on this concept. So here's one example. The square root of 36. Okay, the square root of 36, I'll break that down to the square root of 36 times the square root of -1. That's going to be the same as 6 times I. It'll be written like 6I. Generally, you'll see it written kind of cursive, so 6I is a common way of writing it. On the same token, if I had the square root of 64, that'll break down, and I'll do it down here, which is how we've done it before. That becomes the square root of 64 times the square root of -1. Square root of 64 is a perfect square, so I know it's 8, and the square root of -1 is I. So that's our first idea, is that we can go ahead and get a square root. Now, what about something like this? The square root of -200. Now, when I break that down, I get three separate things. I know that the biggest perfect square in 200 is the square root of 100. Okay? I also know that's going to be times the square root of 2. Then I'll say it's times the square root of -1. We keep that negative outside of it. Now the square root of 100 is 10. Square root of 2, I can't do anything with that. The square root of -1 will give me I, so the convention is to write the I next to the integer and write the square root last. So that would become 10I square root of 2. All right? Now the next thing is, why do we have this system? Why is it necessary to do a complex number, or what we now know as an imaginary number? First is, if I have a parabola, let's say I've got a parabola that looks like this. Y equals x minus 4 squared plus 2. Okay? So I know my vertex would be 4 and 2, and it points up. So I'll do my standard 1 and 1, 2 and 4. And I don't know if I have room 3 and 1, 2, 3, 4, 5, 6, 7, 8, just a little bit past that. Here's my axis of symmetry. So there's 1, 1, 2, 1, 2, and 3 over here. So this is going to look like this. I don't have any roots to this. It does not touch this x-axis down here. But there's times I need to use that. Now, if I was to expand it, I would have had a function that looks like this. Y equals x squared minus 8x plus 16 plus 2. X squared minus 8x plus 18. If I set that equal to 0 and try to solve it with the quadratic formula, this is what I'll get. negative 8 plus or minus the square root of b squared, which is negative 8 squared, minus 4 times a, which is 1, times c, which is positive 18, all over 2 times 1. Now, when I go to simplify, I will now have 8 plus or minus the square root of negative 8 squared is positive 64. 4 times 1 times 18. So I have minus 72 all over 2. This gives me a problem. This becomes the square root of negative 8. So according to this, I do not have a solution. Now, under my new system, I'm now going to break this down, and that becomes the square root of 4 times the square root of 2 times the square root of negative 1, so that becomes 2I root 2. So the solution to this one is 8 plus 2I root 2 over 2. Now that does reduce if I take a 2 out of that. If I divide a 2 out, I have 2 times 4 plus I root 2 over 2. So really I just get 4 plus I root 2. My other answer, I can reduce it the same way. It'll be 4 minus I root 2. 4 plus I root 2. These particular things have a special name called a complex conjugate. We'll get a little further into that later. Okay, so now the concept of a complex number is that it's the combination of a real part of a number A, an imaginary part, they're calling this BI. So then I put two pieces together. Okay, the A is the real part, the BI is the imaginary. An example might be something like this. 5 plus 4I. The real part would be the 5. The imaginary part would be the 4I. Okay? And I made some other notes in here, and we don't need them necessarily, but it's just to once again refer to what a complex number is, that combination. Now, there's some other things. If it is just a, if A is 0, we would have a pure imaginary number, okay? And okay, so we were talking about complex, real, and imaginary here. So we got A plus BI. So a couple quick examples, okay? This is a quick example. This, if I just had this kind of idea, 5I, that would just be called a pure imaginary number that we see here, okay? Because A would be 0. And this is talking about that same thing again. And we want to know about graphing it, okay? Now with graphing it, let me show you how that's going to look, okay? Let me do a new slide and show you some stuff with it. So if I have, what we'll do with graphing is we're going to have two parts, okay? We are going to have a real part. This is called the imaginary plane, and this is the imaginary. Okay, it's supposed to say I there. Let me fix that up. There's the real part and there's the imaginary part. So when we're graphing, what we'll do is we have what's called the imaginary plane. So if I have this, if I have 3 plus 2I, the way that will graph will be, we will, along the real axis, we have 3. Okay, so it'll go 3 to the right. Along the imaginary axis, we have a positive 2, so we'll go 2 up. So if I graph that here approximately, I'll go ahead and call that 5 and this 5. So my 3 and would be here and up to that point is approximately That is how we would label it, 3 plus 2i, right on the graph. Okay? Now, if I wanted to plot, let's say, 4 minus, let's say, 3i, I'll go 4 to the right and down approximately 3. Okay? So what if I want to find the absolute value of this? Now, to find the absolute value, what we will do is this. The concept is I am trying to find out the distance from that point on the imaginary plane back to 0, 0. What I can do is create a right triangle from this. I know the 4 minus 3i was 4 across and 3 up. So in reality, what I'm trying to find out is this distance. We can use our old friend, the Pythagorean theorem. 3 squared plus 4 squared. I find the square root of that. That happens to be 9 plus 16, the square root of 25. We get an answer of 5. Okay? I could have done the same exact thing with this piece. 3 plus 2i. If I draw a right triangle here, I know it's 3 and 2. So my absolute value would be 3 squared plus 2 squared square root. 9 plus 4, that absolute value is the square root of 13. If I try another one, let's try one out here. Let's say I've got negative 6 plus 3i. So I'll say, all right, that's negative 6, and there's up 3. So that's that point right there. So I know this one would be 6 squared plus 3 squared, the square root. So that absolute value is going to be 36 plus 9. So that would be the square root of 45. As we know, that breaks down to the square root of 9 times the square root of 5, or 3 root 5. Getting kind of messy here, so let's clean up a little bit. Let's look at a couple other things with it. Let's do some quick summation, okay? So here was one I did earlier. Okay, maybe a little bit cleaner. So let's look at these notes. Here, I talked about 5 plus 2i. 5 to the right and up 2. Okay? So now go to do that one. It's going to be 5 squared plus 2 squared. So my conclusion about this concept of magnitude would be that in order to find the absolute value of any imaginary complex number, we don't need to worry about the negative sign because absolute value is always positive. So here it's going to be the square root of a squared plus b squared. So I don't even have to graph. The graphing helps us visualize it better. But let's say I've got 4 minus 7i. I will simply say, all right, the square root of 4 squared plus 7 squared. That's the square root of 16 plus 49, which will give me the square root of, looks like it's going to be 65. Now 65 breaks down to 5 times 13. Those are both prime numbers, so we'll leave the answer exactly like that. Last concept I'm going to cover here will be in adding complex numbers. Okay, so for that, we're going to do two things. We're going to add the integers, and then we're going to add the complex coefficients. So if I have this, 4 plus 3i, and I want to take that complex number, I want to add it to another complex number, let's say 2 minus I. I'll first go ahead and combine the integers, 4 plus 2, so I have 6, and I'll add the complex coefficients, the 3 minus 1i plus 2i. And that is my solution. Got a couple other examples up here. Okay, if I had 2 plus I plus 3 plus 4I, I combined them here to show the mental work in there. 2 plus 3 gives you 5. I plus 4I happens to be 5I. All right? Now multiplying is a little more challenging because of this concept. Because what we want to do is we do have I squared being equal to -1. Okay, so when you're multiplying, what we're going to do here is we're going to go ahead and use the FOIL concept, or we're distributing basically, and then change I squared to 1. So if I have 2 plus I times 3 plus 4I, first thing I do is 2 plus 3, 2 times 3, excuse me, which is 6, and then 2 times 4, which gives me 8I, and then I'll convert over to I times 3 is 3, I times 4I is 4I squared. Okay? Now, at this point, we want to look at this 4I squared. I squared itself is equal to -1. So in reality, what's going to go on is 4I squared will be the same as 4 times -1. So what I've really got is, instead of 4I squared, that becomes -4. So to combine them, I've got 6 minus 4, which gives you 2. I've got 8I plus 3I gives us 11. All right, let's try a couple other examples. What about 3 minus 2I times 4 plus 5I? I'll go ahead and distribute. 3 times 4 gives you 12. 3 times 5I, treated just like similar to a variable, plus 15I. Negative 2I times 4 is minus 8I. Negative 2I times 5I is minus 10I squared. All right, now, the biggest challenge in this is that I squared is equal to -1. So I've got -10 times -1. So in reality, that changes to positive 10. So I've got 12 plus 10 is 22. 15 minus 8I will be plus 7I. So there's my solution. I'll do some more on this later. Thank you.